This building is a hybrid timber superstructure on a reinforced concrete transfer plinth and footings. Above the ground floor, everything you see is engineered timber. The structure follows a simple grid, a 5-meter rhythm along the long facades, with 2.5-meter bays at the corners to tighten the edges. This regularity is what allows fast prefabrication and clean coordination with the envelope and MEPs. Loads start at the 280mm lignature slabs. Each slab spans the secondary glulam beams pre-sized at 120 by 360mm at 5-meter spans and 140 by 650mm where spans reach 9.8 meters. From there, the loads go into the 200 by 200mm timber columns and then down through the inclined timber V-frames pre-sized at 300 by 450mm at ground level. Those V-frames concentrate reactions at the plinth, which distributes them to the footings. Slabs are lignature 280mm, acting as one-way plates and as rigid diaphragms, collecting in-plane forces and sending them to the vertical stabilizing elements. Longitudinally, 500 by 900mm beams pick up the longest spans. Secondary 140 by 650mm members are placed transversely every 5 meters. Lateral stability is provided by 3 cooperating elements: the floor slabs that collect in-plane shear, vertical bracings hidden in the facade rhythm and cores, and the V-frames at ground level, which give a wide base and stiffness where the building meets the ground. At the base, timber meets concrete on a plinth. Each V-frame sits on a combined footing sized from an allowable soil-bearing capacity of 200 kilonewtons per square meter, with a pre-sizing of a 3.16 by 3.16 face and 0.70 meter thickness. Tie beams link the footings and manage any horizontal thrust from the V-legs. Structural construction is bottom-up. First, cast the plinth and footings. Then, install the timber V-frames. Drop in primary and secondary beams and columns, and place slabs panel by panel, and then use the sequence floor per floor. The slab chosen for the project is the lignature slab of 280mm, working in a single structural direction. This prefabricated timber system combines strength, lightness, and precision. It offers excellent acoustic and thermal performance, as well as a high degree of fire resistance, all achieved through its internal configuration of timber ribs and insulation. Inside the slab, 42mm of integrated insulation enhance energy efficiency without adding extra layers. Each element arrives on site prefabricated, with pre-cut openings that allow the continuous glulam columns to pass through. These columns are joined with small concealed steel plates connecting upper and lower segments seamlessly while keeping the structure clean and visually uninterrupted. Above the slab, the interior flooring is a 15mm oak finish, chosen for its warmth and timeless durability. In the exterior terraces, the same slab supports a 20mm WPC decking, resistant to moisture and sunlight, yet visually consistent with the interior palette. In wet areas such as bathrooms, the finish transitions to 12mm ceramic tiling, ensuring full water protection while maintaining material coherence throughout the building. Where the slab edges are directly exposed to the exterior at the ground floor sides, we incorporate an additional 75mm insulation layer within the lower cavities of the lignature system. This improves the overall thermal performance and prevents heat loss through the exposed structure. The interior layout is organized through 3 types of partitions, each adapted to its spatial function. In exhibition areas, walls of about 150mm are found, where there is a finishing of oak slats, then FRMDF backing, acoustic felt, insulation, and gypsum on the site, combining material warmth with good sound absorption. In offices and administration areas, partitions are around 180mm thick, with gypsum finishes on both sides, a service cavity, and an insulated core, achieving excellent acoustic and spatial quality. For wet areas and technical shafts, partitions reach 200mm, with moisture-resistant boards, a waterproof membrane, OSB support, and layered insulation, ensuring durability, protection, and stability. Together, these systems define interiors that are precise, prefabricated, and cohesive, where the structure itself becomes part of the architectural expression. The connections, the rhythm of the columns, and the texture of the materials invite people to move naturally through the space, blurring the boundary between structure and finish.
On the first and second floors, the louvers are movable, allowing for precise control of sunlight penetration through the year. During summer, they can be adjusted to seal the interior from excessive heat and solar radiation. While in winter, they open to maximize natural and light warmth. In contrast, on the upper levels, the louvers are fixed, since that area does not require any additional protection. On the north facade, a ventilated facade system has been implemented. This system consists of an external cladding layer separated from the main wall, creating an air cavity that enhances thermal and acoustic insulation. A ventilated facade helps maintain a more stable indoor temperature, reducing energy consumption and preventing moisture buildup. Finally, on the roof, awnings have been installed over the louver structure to protect the roof surface and the mechanical systems from direct sunlight, contributing to greater energy efficiency and equipment durability.
First of all, for the HVAC, we have the pavilion integrates a complete system of heating, ventilation, and air conditioning all in one. It's designed to guarantee comfort and efficiency while respecting the building open and transparent architecture. So here in the ceiling you can see all the machines. So in total we have 5 air handling units. Each one serves a specific fire zone or functional area. I'll show you later in a bit which ones each of them use. So for example, if we continue sectioning here to get to the second floor, here we can see how one air handling unit has this exhibition hall, another air handling unit has this auditorium, and that happens with all the rest of the rooms. Most of them have one air handling unit per area, but some of them use the same air handling unit because it's going to be easier, and the ducts are not that big. For example, the auditorium has very big ducts. That's why it's only one air handling unit, in order to get like the most out of the space that we have. Then most of the ducts come, if not saying all of them, come through this vertical shaft and this vertical shaft. So these two shafts help get all the ducts in order, and it's easier for how the building works. What else can we say about HVAC? Okay, we're gonna show the other. This will be the second floor. This one is big because it has a double height. And then here on the first floor, sorry, this is still the second floor. Here on the first floor we have other 2 areas. This one will be another exhibition hall, the entrance, and then the auditorium has the one above serving its purpose. And then for the ground floor we have this one that it's most the restaurant, and this one that it's more the shop, let's say. And here in ground floor it was a bit tricky because we had these huge beams, so we had to make the installations go so they end up here through the shafts. They go all the way to the top, and they are adapted to the architecture that we have in this floor. So for example, we had a problem here that we needed to go through the beam, so we made this sort of route that the duct could take in order to have, here you can see it clearly, it's under the beam. So maybe we have some problems of the 2.5 meters that we need, but it solves the problem. Maybe we could, because maybe we could make here an oval duct and make it wider than its height in order to get the free height, but this is the solution we came up with. We also have some other arrangements here in order to solve the problem of the beam. Then for rainwater, let's see what we have. So for rainwater, this is the roof. We have the pipes. There's one here, another one here, another one here, and another one here, and the same in this area. Here they go through you can see the green ones here. These ones are simpler. They go all the way down. They're also adapted to the architecture. They go all the way down into this area here. Later in the plan we'll show you better how it works, the whole drainage system. For the drainage, it's very simple. The only one that we could argue there's a problem, it will be in the two bathrooms that we have in here and here, but we solved this by, if we section here, let's see how we solve this. Behind. So as you can see here, we made let's say we dropped the drainage of these two bathrooms, and we made this, there should be a hole in this joist and a false ceiling here in order to get the water, the gray water or the black water, into the, let's see if we can say, into the well, it basically goes to the bottom with this drainage pipe here. So yeah, that's all what we have for installations.